welcome to another module in this massive open online course. So, we are looking at the concept of differential entropy for a source which can take a continuous set of values, alright. So, source alphabet which can take a continuous set of values, alright. Now, let us look at the differential entropy of a Gaussian source, that is a source output which follows the Gaussian, which has the Gaussian probability density function, okay. And this is very important because this is, as we are going to see later, this is one of the fundamental, I mean this is one of the most commonly occurring such sources, or one can say that the source output, one of the most commonly occurring probability density functions for the source output, and has a fundamental role to play in the context of information theory, as we are going to see later. Okay. So, we are going to look at the differential entropy of a this is the differential entropy of a Gaussian source, and this is important because this is one of the most, it is of fundamental relevance in the context of information theory, and it is one of the most commonly occurring practically relevant sources. Practically relevant sources in the sense, frequently, since Gaussian distribution naturally occurs very frequently in nature, the source output source probability, the probability density function of the source output of frequently can be frequently represented using the Gaussian probability density function. Alright, so it is important to characterize the differential entropy of such a Gaussian source. Okay. And as we have known, and as we have seen several times before, no need to repeat it, the Gaussian probability density function is characterized by a bell shaped curve which has the peak at the mean and the spread is proportional to the variance. We have the probability density function, that is 1 over square root of 2 pi sigma square e power minus x minus mu square divided by 2 sigma square. The differential entropy of this source is basically Hx equals minus infinity to infinity log to the base 2 1 over f of x dx. Now, let us simplify this quantity log to the base 2. We would like to simplify this quantity and then substitute it back here. So, let us look at 1 over f of x x, that is 1 over e square root of 2 pi sigma square e power minus x minus mu whole square divided by 2 sigma square. Take the reciprocal, this is simply square root 2 pi sigma square e raised to positive x minus mu square divided by 2 sigma square. And if you take the log to the base 2 of 1 over f of x x, that is basically log natural, the natural logarithm of 1 over f of x x times log e to the base 2, and you can see from this the natural logarithm, well, that is log e to the base 2 times the natural logarithm of square root of 2 pi sigma square e raised to, well, x minus mu square by 2 sigma square, which is log e to the base 2. Now, log of square root of 2 pi sigma square is half 2 pi sigma square plus log e to the power of, well, I am sorry, this is half log 2 pi sigma square plus 1 over 2 sigma square into x minus mu whole square. Okay. So, log to the base 2 this quantity is equal to log e to the base 2 half log 2 pi sigma square plus 1 over 2 sigma square times x minus mu whole square. We have simplified the expression for log to the base 2 1 over f of x. I am now going to substitute this in the expression for the differential entropy to evaluate the differential entropy of the Gaussian source. Okay. So, now what we are going to do, in expression for substitute this in the expression for the differential entropy. What I have is, well, h of x equals minus infinity to infinity f of x x times log e to the base 2 times half ln, that is the natural logarithm 2 pi sigma square plus x minus mu whole square by 2 sigma square times dx. Now, let us look at this term by term. Of course, log e to the base 2, that is a constant. So, that comes out. Okay, times f of x x, let us split the term in the brackets, times half ln dx plus, well, log e to the base 2 f of x x x minus mu whole square by 2 sigma. So, I have split the term into the brackets. So, let us split the term, written it as two separate integrals. And now, you can see that in the first integral, this is a constant, okay, half log 2 pi sigma square, this is a constant. So, this will come out of the integral. And if you look at this quantity, this has a very we will come to this. Okay. Now, let me just rewrite this so that we can look at the entire thing at once. So, this is log e to the base 2 times half log 2 pi sigma square into integral f of x dx plus log e to the base 2. Now, in this 1 over 2 sigma square, this is also a constant in the second integral. So, I can write this as 1 over 2 sigma square minus infinity to infinity x minus mu square f of x dx. And you will observe two interesting things. First, this is equal to 1 because the area under this minus infinity to infinity f of x dx, this is nothing but the area under the probability density function equals 1. Okay. So, this is nothing but area under, or this is nothing but total area under PDF. Okay. This is from the, it follows basically from the definition or the properties of the PDF, follows from, let us say, follows from property of PDF. And if you look at this, this is very interesting. This is integral minus infinity to infinity, integral minus into infinity x minus mu whole square plus where mu is the mean f of x dx. This is nothing but the variance. This is simply the definition. This is the variance. This is nothing but this is equal to the variance, that is integral minus infinity to infinity x minus mu square f of x dx, that is nothing but the second order the central moment of second order, that is the variance of the random variable. Okay. This is for any general random variable, not necessarily only for a Gaussian random variable. This is the definition of the variance of a random variable. Okay. So, now I substitute these, and what I have is basically log e to the base 2 times half ln 2 pi sigma square times 1 plus log e to the base 2 into 1 over 2 sigma square into sigma square, and what you can see is basically the sigma squares cancel, and therefore, I can write this as well, log e to the base 2 into half log 2 pi sigma, half ln 2 pi sigma square. So, I can write this as half log, I can write this as half log to the base 2 pi sigma square, because log e to the base 2 into log 2 pi sigma square to the base e is basically nothing but log 2 pi sigma square to the base 2 plus half log e to the base 2, which is equal to half log 2 pi half log 2 pi sigma square e. Okay. Okay. And this is the differential entropy of Gaussian source, that is output is Gaussian probability density function with mean equal to mu and variance equal to sigma square, and observe that it depends only on the variance. That is something very interesting. It does not depend on the mean mu. That is, you take your Gaussian source, shift the output probability density function by a constant mean, all right. The resulting differential entropy is not different, right. The differential entropy of the source does not change. It does not depend on mu. It only depends on the variance sigma square, and that is very interesting, because if you see, so this is mu the dE does not depend on mu it depends only on the variance. It depends only on the variance, that is a spread, and you can see half log 2 pi sigma square, this increases with variance. That is what you can see is that as the variance increases of this Gaussian, the randomness increases, the spread increases, alright. When its variance is low, then it is concentrated towards the mean, alright. One can say that the randomness or the uncertainty of the source is low. As the variance increases, the spread around the mean or the spread from the mean increases, alright. So, the randomness of the source is increasing, therefore, the differential entropy is increasing or the uncertainty is increasing, and entropy is nothing but a measure of the uncertainty. So, dE increases with variance sigma square, basically because as the uncertainty increases. Okay. So, the differential entropy, so you are observing two interesting things. One is that it does not depend on the mean, that is a shift by a constant factor which affects only the, that is if you shift the Gaussian probability density function by a constant, that is the Gaussian probability density function is just shifted in the mean, the variance remains unchanged, the differential entropy of the source remains unchanged. It does not depend on the mean, and also you can see it depends only on the variance and it increases with the variance. As the variance increases, the spread around the mean increases, the uncertainty of the Gaussian source is increasing, therefore, the differential entropy is increasing. So, these are some interesting aspects. Alright. So, first we have derived the differential entropy of this Gaussian source, which is very fundamental, which is very relevant, has a fundamental relevance in the context of information theory, as we are going to see later when we discuss about the channel capacity, the capacity of a Gaussian channel, a channel with Gaussian noise. And also you can see that has an interesting property that the differential entropy does not depend on the mean and it increases with the variance. Alright. So, let us stop here and we will look at other aspects of the subsequent modules. Thank you very much.